Okay, today we're going to start our discussion on modeling. And what we mean by modeling is identifying what model makes the most sense given a set of data. So maybe you collect data on something. Does it appear to follow a linear, quadratic, or an exponential trend? And there's some things that we can look for. A lot of our work is going to be on the calculator, but even without looking at a calculator, there's some stuff that we can look for. So I'm going to do just like a quick little table here, XY table, and have X go 1, 2, 3, 4, and on Y, 2, 5, 8, 11. Okay, let's do a little sketch of that. Okay, so 1, 1, 2, just as best you can, 2, 5, maybe there, 3, 8, 4, I think I'm up here somewhere, I don't know, can't really tell where my lines are, but there's a linear model, okay? And we've looked at scatter plots before and data before, and this kind of has a linear trend, right? So I look at that and it looks like if I were to connect the points, it would create a line. And I could also have a scatter plot, so linear trends either with a positive slope. So the data is not going to fit exactly, right? But that pretty much looks like it's a line with a positive slope. Versus sometimes we have some data that has a negative slope, all sorts of points. And again, it's not going to be a perfect line when we collect real world data, but pretty close to, okay? So if we're trying to identify from a table, if we have linear, quadratic, or exponential, when we look for linear, what we're looking for is a constant difference. And so what that means is from the table, it should be pretty constant how it's increasing or decreasing by. So I can see +3, +3, +3, and I could maybe predict that the next point would be 14. Okay, that there's kind of this constant difference that's happening from as X increases by 1. Okay, so if I see a table and I'm noticing that the outputs, okay, that really we're talking about our outputs here versus our input. Okay, that our output's having a constant difference as X is increasing by 1. Obviously, if this table jumped around and it went like from 1 to 5 to 11 to -22 for my X values and my output, then the Y values aren't going to be kind of that consistent change. But if I look at X values increasing in the same amount each time, increasing by 1 here, then my Y should also have that constant increase. And we know from when we did linear equations, right, that's our slope that's creating that constant difference from one thing to the next. Okay, so identifying a linear model, that's what we're looking for. For a quadratic model, so quadratic models, if I were to look at a scatter plot or some data that created a quadratic model, it's either going to go up and then maybe come back down. And again, it's not going to create a perfect parabola, it's data, so it's not necessarily going to be perfect. Or could have something that goes down and then maybe comes back up. That looks pretty quadratic, and I'm trying to like on purpose make it not look perfect because your scatter plots won't look perfect. Now what's really cool is that we can look at a table and we can determine if it's quadratic by something that happens. So I'll go 5, -1, -3, -1. Okay, as my input increases, something that happens to my output. So here I have a table. I know that if I were to plot that table, let me try to do my best to plot that table. Just give myself a few points. I have 0, 1, 2, 3, 4, 5. So if I were to look at a sketch, I mean, that's certainly one easy way to see what model I have, but we're really going to wait to try to do that when we're using our calculator. So that's kind of how that plots out. Is I have 0, 5, 1, -1, 2, -3, and then 3, -1. So it starts coming back up there. And there's the beginning of a parabola being formed with this data set. Now, if I do what I did up here, which is look at the difference from one term to the next, to go from 5 to -1, that's subtracting 6. From -1 to -3 would be subtracting 2. And then to go back up to -1 would be adding 2. So I can see that this, if I just had, I have no other information, I just had this table. Looking at that, I'd go, well, it's not linear, right? Because there's not a constant change. If we look at the differences and we see it's not linear, the next thing we maybe want to look for is what's the difference between those differences, or the second difference. And so from -6 to -2, that's adding 4. And from -2 to +2, that's also adding 4. And look at that. Okay, there's something that's constantly happening there. And that will happen when our model, or be really close to happening when our model is a quadratic model. So what happens is we have a constant second difference. Okay, and if that happens, then we know that that's a quadratic, that data is following a quadratic model. For our exponential models, it's something a little bit different. So for our exponential models, those are the equations we've been looking at with our exponential equations and our graphing and our growth and decay. And when we look at a table for our exponential models, we're not going to look at the differences. You may always start with the differences. That's kind of what I do. And then if I notice that, so I'm just giving us some points here. So when I'm given any table, I do kind of start with the differences. So I go through and I'll use a pencil here. And I'll go, okay, so this is 8 less, and then that's 4 less, and then that's 2 less. And then I look at the second difference. I'm just kind of checking. Okay, that's +4, that's +2. And I go, okay, there's nothing happening in the first difference, so it's not linear. Okay, not linear. And this means it's not really following a quadratic model there. Okay. So then I go to, well, could it be exponential? And this kind of thing will happen also when it's exponential, when it's like half, half, right? And I can see it here, half, half, half. Okay, because with our exponential models, what's actually happening is we have a constant ratio. And so, oops, I didn't mean to write an R there, constant ratio. So when I look at my table, I'm instead of looking at the differences, so if I start looking at the differences, I'm like, okay, not finding anything there. What we're actually going to look at is the ratio from one term to the next. So, and I could go either way. So I could either go 16/8, or I could go 8/16, depends on how you want to look at it. So if I go 8/16, that's half, right? And I'm seeing that as I look down. And then 4 to 8 is also half. And 2 to 4 is also half. So we have this constant ratio that's happening from one term to the next. And if that happens, then the model that I want to use is an exponential model. Now, in terms of what our scatter plot looks like with an exponential model, well, it's either going to look a little bit like exponential growth, maybe something like that, or it's going to appear to maybe decay over time, maybe something like that. So when we start looking at scatter plots, we also want to know, what does the graph of each of these look like? Okay. Okay. So now let's look at the next page where we have just a bunch of tables. And we're going to determine what model we have based on that. So I'm going to start by looking at the differences. And then if the differences don't work out, then I'm going to move to ratios and decide what model I have. So looking here, I go from 39 to 36. So that's a difference of subtract 3. And then from 36 to 33, subtracting 3. subtracting 3, subtracting 3. And then at the end, I'm like, well, 27 to 15, that's subtracting 12. Whoa, what happened there? Well, we always want to be aware of what's happening to my inputs. So here I add 1, add 1, add 1, add 1, boom, add 4. So this is only a jump of 12 because it's 4 times -3. It's 4 increases on my input value. So we want to see if our table's not consistent, then looking at the constant difference or the change from one to the next isn't going to matter anyway. Okay, so always just kind of being aware if there's a jump in our inputs, well then our outputs in this case should also jump linearly and it should follow the same pattern, but I'm going up 4, which is why it becomes 12. So I can see that I have a constant difference here. I'm using a pencil. Hopefully that's okay to be able to see, which means this data set follows a linear model, okay? And it's also linear because on your homework, it'll ask you this if it's, trying to think of what the wording was on the homework. If it's linear increasing or decreasing, that doesn't, I don't think that was the words they use. Let me look. If it was linear growth or decay. And so I can see here that I'm decreasing with each increase in my X value. So this is linear decay. Okay, it's going down, subtracting 3 each time. Okay, let's look at our next one here. So constant difference from here to here, I'm subtracting 1.5. And from here to here, I'm subtracting 2.5. And from 4 to 0.5, I'm subtracting 3.5. And then I'm subtracting 4.5. So the first difference is not consistent. But then if I look at the second difference, so here's our first difference. If I look at the second difference here, so from 1.5 to, from negative 1.5, I should say, to negative 2.5, I'm decreasing by 1, decreasing by 1, decreasing by 1. So I notice that I have a constant second difference, which means I have a quadratic. Okay, constant first difference is linear, constant second difference is quadratic. And then if I, instead of having differences, I have a common ratio, then that's exponential. Now, just like here where it says linear decay, I can say it's a quadratic with a maximum or quadratic with a minimum. So I have to kind of think about how these points, and you don't have to plot them necessarily, but just kind of think about what they would look like. If I'm at 1, 8, and then 2, I'm a little bit less, and then 3, I'm a little bit less, and then 4, I'm a little bit less, and then 5, I'm even still a little bit less. Okay, that's, no, it's not really showing me quadratic, is it? 1, 8, 2, 6.5, 3, 4. That one's not a good example because it doesn't turn around. It doesn't give us a turnaround, but on your homework, you'll be able to see if it's turning around and if it's creating a parabola like this, or I'll erase this one because that didn't help us very much with the points that were given to us. We know it's quadratic because of the constant second difference. We just can't see if there's a maximum or a minimum. So on your homework, you'll be able to see in your table, is it going up and then starting to come back down, or is it going down and coming back up? And so this would be with a maximum, and this would be with a minimum. So all we know is that it's quadratic right now. Without more data, we wouldn't know where it's turning. I would think it's a minimum. It looked like it was about to go kind of curved, was curving that way a little. Okay, let's look at our next example. So our first difference here, if I just start that way, so if I go 162 to 54, that's subtracting 108. And then from 54 to 18, that's subtracting 36. And from 18 to 16, that's subtracting 12. and from 6 to 2, that's subtracting 4. Okay, so there's my first difference. Then if I look at my second difference, and hopefully you can see it before we even start, from 108 to 36, I'm going back up positive here, so I'm adding 72. And from 36 to 12, I'm adding 24. And I can kind of quickly see here, I'd add 8. That neither the first difference or the second difference seems helpful here. So, okay, what if we looked at the ratio? Go over here and look at the ratio. From 54 to 162, 54 over 162, when I look at my calculator, is 1/3. Okay, reduces to 1/3. 18 to 54. 18 to 54 also reduces to 1/3. 6/8 also reduces to 1/3. 2 6 also reduces to 1/3. And like I say, you can kind of go 2 to 6, 6 to 18, 18 to, or I could have gone this way and it would have also had a ratio of 3, 162 over 54, 54 over 18, 18 over 6, and 6 over 2. It's just, I'm seeing that as it increases, it's decaying over time. So I want the actual ratio. So if you go bottom up, it's going to give you your actual, like decay should be less than 1, growth greater than 1. So I can see that this, it does not have a first difference, does not have a second difference, but does have a common ratio. Common ratio, which means it would be exponential. And it would be exponential decay. I can tell that because as my input increases, as I go up by 1 here, this is decaying, becoming less. So there are 3 more tables here, and I'd like for you to pause the video and try to determine what type of model do you have? Do you have linear, quadratic, or exponential, given the table that you have? And don't plot the points. Look at first difference, second difference, or common ratio. Those are the things you're looking for. Okay, so let's see how we did here. So looking at my first table, my first difference is not constant, but then if I look at my second differences, I see that it's consistently increasing by 4. So I know it's quadratic. I can't tell based on the data that I have if it's turning there or not. If I put it into a scatter plot, I might be able to tell a little bit more if it's curving down. Then I know it would be a minimum, but quadratic is what we have for there. Then here, my difference is my constant first difference, which tells me that I have linear, and it's increasing as x increases, y is increasing, so it's linear growth. On our last table, first difference is not consistent, second difference is not consistent. If I start looking at the ratios, I get 1.3 for all my ratios, so 64, I kind of didn't skip the last one, over 48, 48 over 36, 36 over 27. So constant ratio tells me it's an exponential model. And I can see that as my input increases, my output increases. So it's exponential growth.